to increase the transmit power. And we have to increase the transmit power so that in the worst case, is this one, we still have above or at S0. And since the power density is directly related to the transmit power, if we increase the transmit power by this factor, all this speed is 0 in free space, the minimum received power will be 0.462 times 2.16 S0, so it will be S0. Is it clearer? Yeah. Okay. This is the first countermeasure. Now we will see those a series of countermeasures to compensate. This is called power control. You increase the transmit power to compensate for the effect of the reflection. In a sense, this is a brute force approach, because you simply increase the power by using force. The trouble is that to increase power, when you need a bigger transmitter, you need more power, consume more energy. So it works, but it's an expensive system. Now, the brute force approach, like power control, does not always work. And this is the topic of the next exercise, the next application exercise. That we will see another countermeasure. The problem is as follows. Again, we have transmitter, a receiver, and a ground reflection. Now, this is a typical microwave link situation. We have towers. This is H2, and this is H1. The distance between the two stations is 50 kilometers. And you have one antenna here, one antenna there. So I give you the parameters of the link so you can. Frequency is 20 gigahertz. As I said, H1 is equal to H2 is equal to 25 meters. And we are in a nasty situation because the reflection coefficient of the ground, the absolute value is 1. So the reflected electromagnetic path has got exactly the same power, the same amplitude, as direct path. And phase is random. Now the trouble is, in this kind of situation, where you have a very strong reflection coefficient, the brute force will not work. Why? What will be the minimum electrical field at the receiver in this situation?
Is zero.
And there is nothing you can do by improving by increasing the transmit power to cancel the zero. So in this kind of situation, you have to be more clever and adopt some other countermeasure that is not brute force. There are two possible. We will see two possible countermeasures. One countermeasure is antenna diversity. The antenna diversity works like this. You install a second antenna as a receiver. In a position so that, let's call this antenna B, and let's call this antenna A. Antenna diversity works in this case like this. If in B, at the antenna, at A, antenna, we have a perfectly destructive combination. Combination of E0 and obviously the reflected one. If this happens, then we must be sure that in B there is a positive combination. Constructive combination. So then the receiver chooses whichever antenna is working at that time. Now the exercise is calculate this height so that this happens. You have to calculate how higher than the first antenna you have to put the second antenna on the tower, so that you are sure that if A we have a destructive combination, in B we have a constructive combination. I give you a hint, you have to think about the difference in path lengths. And in particular, the difference of the differences. Think about it and then we solve it together, as usual.
cagar. Porque significa que se llega chévere. Pero la que se llega nada puede ser la misma, pero con base random. La cosa es que estoy fase random, es menos 180. Entonces te llega a tener, o sea, no, fase random es que está cambiando todo el tiempo. Pero puede llegar a no puedes mostrar yo, más apenas no puedes hacer taller. Acá este error no era uno de los otros. Entonces aquí puedes mejorarlo subiéndole los paneles que llegaba. Pero acá, más que más, si no puedo hacer menos. Lo hace como que 1 menos 1 o 2 menos 2. Lo que hace es que mantenemos arriba. Que mientras este lea menos 180, acá le hace pero sabía, estamos viendo mejor caso y mejor caso. Que obviamente que esto es random, se empieza a cambiar, siempre uno de los dos va a estar cogiendo.
I will be perfectly accurate. Okay, how do we solve this? Let's think about the path differences between reflected electromagnetic ray and the direct. Those differences will be different for A to B because the geometry is different. So, for the A antenna, the difference between the reflected and direct electromagnetic rays, those two here, that reach the antenna, has got the usual expression 2H1 H2 divided by 2. And for B, only thing that changes is that H1 will be, the height will be increased by that H1. Now, what is the difference in phase? This is the path difference. Difference in phase. Will be obviously the propagation constant for A with times delta A and plus an unknown phase contribution from the ground. This phase difference is due to the difference in path length, and there is an additional contribution that we don't know due to the phase of the reflection coefficient. Because please remember that the reflection coefficient multiplies everything. So any phase contribution due to the reflection coefficient will be found in the phase difference. Here we will have beta delta B plus the same terms of phase. And we know that this is, when this is perfectly destructive, this must be constructive. Destructive means out of phase, pure odd numbers P. This constructive will be pure even numbers of P. So the phase difference between the phase differences must be P. If we want this to be constructive when this is destructive, the phase difference of the phase differences must be big. That is, phase difference of the phase differences. Obviously, you will soon discover that it is irrelevant. And if you collect you can simplify the P, and what we have said also translate into the difference in the path differences must be difference between the path differences. And this condition now allows us to determine the unknown, because we take this, put it in that equation, and we solve for the unknown that is delta H1. So what we get is and from this you can get delta H1 that is equal 7.5 meters by calculating. You need the wavelength. Obviously, the wavelength is the speed of light divided by the frequency. It's actually quite small because it's is 1.5 centimeters. Even if the wavelength is so small, you need quite a large separation of the antennas, vertical separation of the antennas, to accomplish the goal. Okay. Question, please. Is it clear? No? No one be happy to explain it again. Otherwise, I assume that everybody is active. Yes, please.
I don't get it. Where you get beta delta dB plus.
You don't get this one?
No. Lower. That one.
That one?
Lower.
Oh, okay. Now, this one comes actually from here. That is, you know that the contributions as far as the A antenna are destructive. So their phase must be, phase difference, as stated here, must be T. You want, in this situation, in this condition, the phase difference to be 2P. So if you take this minus this, you take this minus this is equal to this minus this. You subtract the two expressions. 2P minus P is equal to P. Okay, you do this minus this. More questions? This kind of countermeasure is normally used on microwave beams to counteract for the effect of the ground. Also because in this situation, brute force approach does not work. Okay, can I wipe up? Okay, these techniques requires you to install a second antenna that is higher than the normal one. What do you do if you cannot do that for whatever reason? You can use another technique, another countermeasure that is called frequency diversity. Also called frequency hopping because you change frequency. Now, the exercise is exactly the same, but you cannot install another antenna. Frequencies change, this kind of thing, but the idea is the same. You have a direct and a reflective part. Transmitters and receiver. Now the data of this problem are slightly different because frequency is different. Is 6 gigahertz. H1 is equal to H2 is 100 meters, so those are quite tall communication towers. And the distance is 50 kilometers. Now, what we do in this situation is that, let's call this frequency F0. Now, at frequency F0, we experience a perfectly destructive combination of the electromagnetic waves. We don't have a second antenna, but we can change frequency. We can move from the frequency F0 we can jump to a frequency that is F0 plus delta F or F0 minus delta F. We can change frequency. And the question is, what is the value of this jump? That guarantees a perfect constructive combination. So at F0 we have a perfectly constructive combination. We change frequency, and I want to know exactly what is the frequency that gives me a constructive combination. So at frequency plus or minus, the same thing, we must experience a constructive combination. Few minutes to think about it.
Los dos son diferentes. Por eso que bueno, está diferente.
Sì, ma no, non importa. Okay. Now, in this geometry, the only thing that changes is frequency. So let's first of all calculate the usual path difference. Between direct and reflected. And we will discover that the difference is not a huge number. Because as usual it is 2h1 h2 divided by d. Now the towers are 100 meters. Divided by 50 kilometers. So it is quite small, only 40 centimeters. There is only a very small difference, only 40 centimeters of difference between the direct, the reflected path and the direct path. Please note that we are talking of distances of 50 kilometers. But that's the geometry. As I said, even if this number, 40 centimeters, is much smaller than 50 kilometers, when we talk about the phase of the wave, it can be important. Because you have to, in case of phases, you have to compare this number with wavelength. Okay. But let's go back to our problem. The difference in phase between the direct and reflected electromagnetic ray will be beta delta plus an unknown contribution from the ground. To be divided lambda 0 delta plus, where lambda 0 is the wavelength calculated at frequency f0. It is this delta phi0 with the now it is clear that if you change the frequency, the difference in phase changes. Because if you change frequency, you change the value of beta. So this is what is happening at frequency f0. Then you change frequency and you go from f0 to f0 plus delta f. In this case, it is simple. You just changes Now, as usual, if here there is, sorry, this is what's happening at frequency 0 plus delta. Now, if at this frequency we have a destructive combination, means that this number is big. And we want to have a constructive combination. We want that phase rotation at this other frequency is 2. And as we have done before, we simply subtract the two expressions and we get very simply 2p delta f divided by c is equal to p. Because there must be a delta somewhere. Sorry, I forgot this delta. Is that the delta? Blackboard effect, close. Because those terms cancel. So you can solve this equation immediately for the jump in frequency. That is C divided 2 times 2h1 h2 divided by b, or 0.4 we already calculated it. You get 375 megahertz. Not much with respect to 6 gigahertz. So you have to change your frequency slightly from 6 gigahertz to 6.275. And you go from a completely destructive situation to a perfectly combining situation. Questions? There is another countermeasure technique that we will not discuss now, we will discuss it later. Because it is not working well in this situation. It's more a technique that you use in mobile systems. And this, I anticipate, it is polarization diversity. You change polarization. Does not work too well in this combination. No questions. Okay. At the end, I have a question for you. Don't have a question. But at the end of today's day. Okay. And again, still on the effects of the ground. System availability. Now, the goal of the next exercise is to evaluate what is the percentage of time when your system is working, when you have a strong reflected electromagnetic wave and you cannot completely compensate for it. Let me be more precise. At the receiver we have a direct electromagnetic ray and a reflected electromagnetic ray. Unfortunately, they have the same amplitude. That is, the reflection coefficient of the ground is 1 and the phase is random, and it is distributed in a uniform way. It's a random number between 0 and 0. Uniform distribution. You cannot adopt any particular countermeasure, but having